Very well. Welcome, everybody. So we're going to continue talking about linear differential equation with constant coefficients. So what we learned so far? We start talking about, well, differential equations with one solution given. If we have one solution like y sub 1, then we can use the method of reduction of order. To find the second solution, which is linearly independent from y1. So you get y2, which is equal to y1 times u of x, another function. And in your homework, you saw that sometimes this gets very messy. Where is my eraser? Sometimes it gets very messy if you want to apply the direct derivatives and then plug them back into the differential equation. You can use a shortcut as well. So your shortcut says y2 is equal to y1 times the integral of e to negative integral px dx divided by y1 squared, and you're taking the integral with respect to independent variable. But just note that when you're applying the shortcut, you have to have your second order differential equation written in standard form. It means that you have the second derivative of y plus px y prime plus qx y equal to 0. So the method of reduction of order, again, you can just start taking the first derivative, taking the second derivative, and then substitute that into the second order differential equation that you have. Or as you saw, for example, in question 15 on the homework, it gets very messy. You have a lot of terms to combine. You have a denominator, which is very messy. So instead, we can apply the shortcut. Shortcut says, as long as you have y1 and you have your second order differential equation in standard form, y2 is nothing but y1 times the integral of e to the power negative integral of px dx divided by y1 squared dx. Well, and in many cases, we do not even have the first solution. We start classifying the second order differential equation into the linear differential equation with constant coefficients. If y1 is not given, and we have the general case that we have a1, a, the second derivative of y, plus b, y prime, plus cy equal to 0, constant coefficients, then we can form something that we call auxiliary equation. In some other books, they call it characteristic equation. So form auxiliary or characteristic equation. It comes from that e to the power mx is a possible solution for these types of differential equations. By taking the first derivative, second derivative, and plugging to the differential equation, we have a m squared plus bm plus c equal to 0, which is nothing but a quadratic equation that we saw in algebra. By solving this equation, we have the following case. The first case was that you solve this equation and you have two distinct solutions. M1 and M2 are distinct solutions, real solutions. So in that case, they say that, hey, the general solution for this homogeneous differential equation, y is equal to c1 e2 m1x plus c2 e2 m2x. Later on, we're going to see that when we are dealing with homogeneous linear differential equations, we're going to put a little index as c for y and say that, hey, the general solution for homogeneous differential equation is written this way. 2. The second case was you have repeated solution. M1 is equal to M2 repeated solution. Well, in this case, the general solution for homogeneous differential equation is equal to C1 E2 M1x plus C2 times x E2 M1x. And finally, if we have conjugate complex solutions, 3, M1 is alpha plus I beta, and M2 is alpha minus I beta. Well, in this case, the general solution for homogeneous differential equation is written as e to power alpha x parentheses C1 cosine beta x plus C2 sine beta x. Okay. Now I expect you to ask, well, what if I have a differential equation of order 3 with constant coefficients? What if I have a differential equation of order 4 with constant coefficients? Can I apply the method of auxiliary or characteristic equation to solve it? Question. Can we apply this method? What method? Auxiliary equation to higher order linear differential equation with constant coefficients. Let us take a look at one example. So we want to answer this question. Let us try one example, see if we can apply this method to this differential equation of order 3, of the third order. Very good. Example. Solve the third derivative of y plus 3, the second derivative of y, minus 4y equal to 0. Okay, what should I do here? I have a third order. This is the third order. Linear homogeneous differential equation. Do I have constant coefficients? Well, take a look at this. Here you have 1 as the coefficient of the third derivative of y, 3 times the 3 as the coefficient of the second derivative of y, and you have just a coefficient which is just a number of y, and the right hand side you have 0. So it is a differential equation with constant coefficients. Let us form auxiliary equation or characteristic equation for this differential equation. Let us construct the auxiliary or characteristic equation. So by substituting y equals to e to mx, y prime is m, e to mx, the second derivative is m squared, e to mx, and the third derivative is going to be m to the third, e to mx. I'll just do the substitution. This guy becomes, here you have m to the third, e to mx plus 3 m squared e to mx. And here you have minus 4y, which is e to mx equal to 0. So if you factor out e to mx, then you're left with m cubed plus 3 m squared minus 4 equal to 0. And e to mx is not 0. So it means that this quantity, this equation of degree 3 is equal to 0. M to the third plus 3 m squared minus 4 equal to 0. What's the solution or solutions for this equation? Very well. So this is what we did last week. We had a differential equation, second order differential equation with constant coefficients. We say that the possible solution is y equals to e to mx. We take the first derivative, we take the second derivative, we plug into the original differential equation, and we form an equation that we call characteristic equation or auxiliary equation, and we start solving that. We want to know if we can apply this method to higher order differential equations with constant coefficients. So we say that suppose e to mx is a possible solution for this differential equation. We take the first derivative, we take the second derivative, we take the third derivative, and we plug them back into the original differential equation that we have. So start simplifying the whole thing. E to mx is never 0, so it means that this equation of third degree is equal to 0. Just going back to algebra, all right? In algebra, by inspection, well, m equals to 1 is one of the solutions. By inspection, m equals to 1 is one of the solutions. So you have 1 plus 3, which is 4, minus 4 equal to 0. How do we find the second solution? We're going to do long division. Long division. So by doing long division, here you have, let me see, m minus 1, and here you have, let's see, m cubed plus 3m squared minus 4, and this is going to be m minus 1. So m squared, you get m cubed minus m squared minus plus, and you get 4m squared minus 4. So plus 4 plus 4m, you get 4m squared minus 4m. Subtract, you cancel out these two, you get 4m minus 4 plus 4. 4m minus 4, which is just 0. So this guy can be written as just pure algebra. M minus 1 times m squared plus 4m plus 4 equal to 0. We broke down this equation of degree 3 into the multiplication of a linear term and a quadratic term. Algebra, going back to intermediate algebra. So by solving this, you get m minus 1 equal to 0, m is 1, and by solving this, you get m plus 2 squared equal to 0, so m equals to negative 2 is repeated solution. So what are we going to do? We're going to start writing the solution for this differential equation as m equals to 1 is just gives us e to power 1x. Y equals to e to power mx, m is 1. So the general solution can be written as c1 e to power 1x plus. Now from m equals to negative 2 as a repeated solution, we have the following. Remember that. This guy is, for example, c2 e to power negative 2x. This is the way that we wrote it down as we explained it last week. Negative Let me just write down the general form like this case, mx plus c3x e to power mx. M in this case is -2, so plus c2 e to -2x plus c3x e to power -2x. We found the general solution for this differential equation. General solution for the homogeneous differential equation with constant coefficients of degree 3. Let us make it more interesting. Suppose I ask you to solve this differential equation. Very good. So question says, solve this guy. 3 times the third derivative of y plus 5 the second derivative of y plus 10y prime minus 4y equal to 0. Okay. So as you can see, we have a third order linear homogeneous differential equation with constant coefficients. What would be our first step? Our first step is to check to see if we can apply y equals to e to mx, and later on its combination for a solution for this differential equation. What do we need? We need the first derivative, second derivative, and third derivative. So let us continue taking the derivatives. Y prime is m e to mx. The second derivative, m squared e to mx. And the third derivative is m cubed e to mx. Very good. Now just plug everything back into the differential equation that you have. You get 3m cubed e to mx plus 5m squared e to mx plus 10m e to mx minus 4 e to mx equal to 0. Using algebra, e to mx is factored out, 3m cubed plus 5m squared plus 10m minus 4 equal to 0. This guy is not 0. So it means that this equation, auxiliary equation, characteristic equation is 0. So 3m cubed plus 5m squared plus 10m minus 4 is 0. We're trying to break this guy down the way that we can solve this. So first, by inspection, we need to find a possible solution for this equation that's going to be the factor that we have, a linear factor. Then by doing the long division, we can find the rest of the factors. So inspection. So inspection to find a possible solution for this differential equation, we're going to form some possible fractions. Going back to algebra. We say that, hey, the possible solution is of the form of P over Q. What is P? P is going to be related to your constant, and Q is related to leading coefficient. Very well. So P is going to be a factor of -4. Just going back to algebra. P is a factor of A sub 0, which is -4, and Q is a factor of AN, which is 3. Okay. What are the possible values that we have? The possible values that we have, factors of -4. Factors of -4 are ±1, ±2, and ±3. Factors of 3 are ±1, ±3. Oh, this is why I wrote down 3. I don't know. Very good. So what are the possible fractions? We have to list all of the combinations. P divided by Q. P over Q can be ±1 divided by ±1, which is ±1. ±2 divided by ±1, ±2. ±4 divided by ±1, so ±1. Now we start doing the division for 1 and 3, 2 and 3, 4 and 3, plus minus a third, plus minus 2/3, and plus minus 4/3. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible 0 for this equation. These are possible. We are not sure which one, but we know all the possibilities. These are all possibilities. It means that we have to start plug in each one of them into the equation and check which one is a 0. So the correct answer is a third. We check all of these possible combinations in forming the quotient, and a third is solution for this equation. Why is that? 3 times a third to the third power plus 5 times a third to the second plus 10 times a third minus 4 is 0. Okay, we found one solution. M is equal to a third. What's the meaning of that? It means that M minus 1, so M minus 1 is a factor of this expression, 3m cubed plus 5m squared plus 10m minus 4. So how do we find the rest of the factors? We have to do the long division. By doing the long division, here we have, let's see, 3m cubed plus 5m squared plus 10m minus 4, and they're dividing this guy by m minus a third. M minus a third. So step by step, we're trying to find what is missing. So first of all, we need to have 3m cubed, so we're going to multiply that by 3m squared. We get 3m cubed minus m squared, and we're going to subtract these two. So minus plus, if you cancel out these two, we get 6m squared plus 10m. So what's missing? 6m is missing, multiplied by 6m. So we get 6m squared minus 2m, do the subtraction, you get 12m minus 4. So here you have plus 12. You get 12m minus 4, do the subtraction, the remainder is 0. So what's the meaning of that? It means that your auxiliary equation, your characteristic equation can be written as m minus a third times 3 m squared plus 6m plus 12 equal to 0. This way we can find the solution for this differential equation. So by solving this, m is a third. If you factor out 3, you get 2m plus 4. 3m plus 4. Okay. So solving this, you get m equals to -2 plus minus square root of b squared minus 4ac. So our discriminant is going to be negative divided by 2 and becomes -2 plus minus, here you have, let's see, 2i square root of I 3 square root of 3 divided by 2. So m becomes -1 plus minus I square root of 3. As you can see, to solve this equation, you get complex conjugate. You have m1, which is alpha, -1 plus I square root of 3, and m2 is -1 minus I square root of 3. So if m is equal to a third, the solution e to mx can be written this way. C1 e to power a third x. By solving this, you get plus e to power -x, parentheses, C2 cosine square root of 3x plus C3 sine square root of 3x. So we found the general solution for this differential equation this way.